All right, so again, good afternoon. Our aim for today is how do we graph complex numbers in moduli. This might seem tangential because, we've been talking about polar coordinates, but you're going to see that, tomorrow we're going to see how to write polar coordinates in complex form, or sorry, vice versa, write complex numbers in polar form. So as a refresher, we're going to talk about complex numbers today. And what you do now is just to graph the following two complex numbers, so 2 plus 3i and 3 minus 2i. And yeah, this should be pretty straightforward. Hopefully you remember how to do that. Just take like, uh, say 20 seconds to do. Just copy this and then complete the do now. Okay, so there's a lot of material I want to cover today, so let me go ahead and review the do now. So again, that was just to, yeah, just graph these two complex numbers. Should be pretty straightforward. Okay, so here is the first complex number. It's 2 plus 3i. So you go to the right and then 3 up. So in the complex plane, when you're graphing complex numbers, right, the horizontal axis is going to be the real axis, and then the vertical axis is the imaginary axis. Okay, so like 2 plus 3i. So this 2 will be the x coordinate, the horizontal coordinate, I mean, and then the 3 will be the vertical coordinate. And then for the other coordinate, it's 3 minus 2i. Don't mind this one. This is the sum, which is another point that the textbook graphed. So the other one is right here. So 3, you go 3 to the right, and then 2 down for negative 2i. Okay, so these are your 2 points right here. Okay, all right. Does anyone still need to copy this? Please speak up or type in the chat. All right, if not, I'll move on then. Okay, so again, today is going to be a refresher on complex numbers. The reason we're talking about complex numbers in our polar coordinates unit is because tomorrow, again, we're going to see how to write complex numbers in polar form. Okay, so here's just a summary of graphing complex numbers. Can someone read this slide for us, please?
Complex numbers a plus bi have two components, real and imaginary. Therefore, to graph complex numbers, we need two axes, the real axis and the imaginary axis. The plane determined by these two axes is called the complex plane.
All right, thank you for that. So yeah, two components, real, imaginary. A is the imaginary, or sorry, A is the real part, B is the imaginary part, and then therefore we're gonna need two axes, right? As we saw in the do now, right? The real axis, imaginary axis. And instead of calling it the Cartesian plane, which we had for like x and y, here we're gonna call it the complex plane. Okay, for complex numbers. All right, is anyone still copying the slide here? You know, speak up or type in the chat. Okay, if not, then I'll move on. Okay, so next is just some questions regarding graphing sets of complex numbers. So in the do now, we saw how to graph, you know, specific points, but you know, we can also graph sets of complex numbers, which is going to require a little more thinking. And normally I would have you complete this on your own for a sec, but you know, since we have shortened periods, I will go ahead and just review the solutions. Okay, so let me scroll up to the answers. All right, so here was the first set of questions. Okay, so how would you describe the set a plus bi? This vertical bar just means such that, so that's what it means in mathematical notation. This vertical bar again, just translated into English, just such that. Okay, a is between 2 and 3 inclusive. So how would you describe that set? Well, you just think about it for a sec. It's the set of all complex numbers whose real part, right? Because it's a, right? A is the real part. Set of all complex numbers whose real part is between 2 and 3 inclusive. Okay, that's pretty straightforward. To graph it, it's going to be the vertical strip, as you see in this diagram, on the real axis from 2 to 3. Okay, and we're going to include 2 to 3, 2 and 3, because again, those values are included here. So all the complex numbers with a real part of between 2 and 3. That's going to be this vertical strip here. Now for part C, if you wanted to graph that same set, but this time, you don't include 2 and 3, it's the same graph, the same vertical strip, but the vertical lines are not going to be solid. They're going to be dotted this time. And I didn't draw that here, but yeah, if you just imagine, instead of solid lines, they're going to be dotted to denote that 2 and 3 are excluded values. Okay. So again, for the sake of your notes, please just copy this down. Yeah, these answers, these three, and then also this diagram here. All right. Is anyone still copying this? No. Otherwise, I'll move on. Okay. So next set of questions was the first part of the group work, which again, I won't have you work on it on your own just because we have shortened periods, but I'll just go through it with you right now. So let's graph the following. The first set is a plus bi such that a is greater than or equal to 0. So again, this is the real part such that the real part is the real part of the complex number, I should say, is positive or 0. Okay. So, again, the real part is the horizontal axis. So any complex number to the right of the vertical axis is going to have a real part greater than or equal to 0. And this y-axis is included, or I should say the imaginary axis. Right, so that's this shaded green part. Okay, so positive, all complex numbers with positive a values, positive or 0. So that's part A. For part B, this one has two conditions. So here we have the set of complex numbers such that a is less than 1 and b is greater than or equal to 0. Okay, so let's break this down into two steps. So first we're going to have a is less than 1. So that's this green part here. These graphs are from Desmos, by the way. So this first part is a is less than 1. So any complex number with a real part less than 1. So that'll be this this green chunk here. I know it's there's also a purple shading for the other condition, but yeah, this green set here. Let me this green. Okay, and then the border is going to be dotted because a is less than 1 and 1 is not included, right? So that's why I have this dotted line here. The other set is b is greater than or equal to 0. So that's going to be the positive values, right, above the real axis. Okay, that's the purple region here. Okay, so this is solid because 0 is included, and then anything above this purple line is b is greater than or equal to 0. Okay, but right, our final answer is going to be the overlap. So I'll shade that in white. So this is the solid line here. And then here we have dotted lines here. And yeah, so the overlap would be this region here. Okay, so a has to be less than 1, and the imaginary part has to be greater than or equal to 0. Okay, so that's this region right here. Okay, does anyone still need this part of the lesson? Otherwise, I'll move on to the next slide. Okay, I'm gonna move on then. Okay, so the first half of this lesson was we're talking about graphing complex numbers as well as sets of complex numbers. The other thing I want to talk about today is the absolute value or the modulus of a complex number. For that, I'll get to the slide. And yeah, that was the word in the do now, by the way. So moduli. Yeah, that's just a fancy word for the absolute value of a complex number. Okay, so I believe Dorothy, you wanted to read earlier. Can you read this part here?
Sure. The absolute value modulus of a complex number. The absolute value of a real number can be seen as its distance from the origin on the real number line. For example, the absolute value of -3 is 3 because it is 3 units away from 0. Likewise, the absolute value modulus for a complex number is its distance from the origin.
All right, thank you for that. So yeah, this is just harking back to the concept of an absolute value. So normally for absolute value of a regular number, like a real number, that's just the distance from the origin, right? So the example I give here is like the absolute value of -3 is 3 because it's 3 units away from 0, right? That's just the definition of absolute value. And likewise, if we talk about the absolute value of a complex number, complex numbers have two dimensions, right? A real part and imaginary part. So it's still going to be the distance from the origin though. And the way we're going to get that is, if we have a general complex number, a plus bi, you can, create a right triangle using the two components. So, if you have b here and you have a here, right? So we can create, there's a right triangle, and you can use the Pythagorean theorem to solve for this length from 0 to the complex number. Okay, and that's going to be square root of a squared plus b squared, right? Just using the Pythagorean theorem, right? A squared plus b squared is equal to the magnitude of, or I should say the distance of this complex number from the origin squared, and then you take the square root of both sides, you get that, square root of a squared plus b squared. But yeah, let me scroll down for the actual so that's what it's going to be. Okay, so the absolute value or modulus of a complex number, z equals, which equals a plus bi, is, notice that we use the same notation, so just vertical bars around the number, and that equals square root of a squared plus b squared. Where a is the real component, b is the imaginary component. Okay. Is anyone still copying the slide here? Type in the chat or speak up. Okay, if not, then I'm going to move on to the next slide, which I believe is the last one. All right, so we have a bit of time left, so why don't you go ahead and try solving these questions on your own. Okay, so first calculate the moduli, which from the last slide we know that's the distance from the origin, so you're going to use square root of a squared plus b squared, and then from there see if you can graph. So we're going to tie these two concepts together, graphing complex numbers or sets of complex numbers, and then tying that concept to the modulus of a complex number, which is the distance from the origin. Okay. Yeah, so take a minute to do that. You want to be able to go over all the questions. So yeah, see if you can solve these. Okay, I know that wasn't too much time, but just want to ensure that we have time to go over all the questions. So let me scroll up to the solutions. All right, so the first two questions were, calculating the modulus of these two complex numbers. First one is, square root of -7 squared plus 24 squared, which is going to be 25, right? You can use your calculator, or if you remember that, that's a Pythagorean triplet, right? It's going to be 25 either way. Okay, so first answer is 25. Part B, we have Z2, the second complex number is 40 plus 9i. That'll be square root of 40 squared plus 9 squared, which is 41. Okay, so that's 41. The other questions were a little more difficult. But yeah, you got to think about it for a sec. So this is a set of all complex numbers, part A, set of all complex numbers such that the distance from the origin, right, that's what absolute value means. The distance from the origin is equal to 1. Okay, so if you think about that, all complex numbers whose distance from the origin is 1, right? And as we know, the complex plane is, 2D, and someone's ringing my doorbell. I won't get that. Yeah, so that's going to be 1, and that's going to be a circle. with radius 1, right center of the origin, right? So that's my description right here. Okay, actually, let me be right back. I'm gonna get the door. All right, sorry about that. Part B is a set of all complex numbers such that the distance is greater than or equal to 2. So if you imagine, right, so basically all these questions have to do with circles, and just think about whether to include the circle itself, shade outside or inside the circle. Okay, so this is going to be greater than or equal to 2. All right, so this is going to be outside the circle, right? Because we need all complex numbers whose distance is greater than 2 or greater than or equal to 2. So you're going to shade the circle itself and then shade outside. All right, so part B, it's a set of all complex numbers whose distance from the origin is greater than or equal to, that should say 2. Sorry about that. 2. Okay, so that's part B, this one right here. For part C, it's the set of all complex numbers such that the distance is less than 1. Okay, so it's less than 1, which means we're going to shade inside the circle. Okay, so this region here is the set of all complex numbers whose distance is less than 1. And note that the circle itself is dotted because we're not going to include the circle because this says less than 1, not less than or equal to. Okay, that's part C. Set of complex numbers whose distance from the origin is less than 1. This is a filled-in circle whose outer radius is dotted so as to not include absolute value of z is 1. Okay. Okay, with that being said, let me just close with announcements. Per usual, there's SGI today, 2:47. Secondly, our next quiz is this Friday, so please check Google Classroom for the topics list. There's also a practice quiz on ALEKS. And third, there's, I posted the details for the group project, so please email me about your group members if you haven't already. Please do so by Saturday. And yeah, check out the other details about the project on Google Classroom. Okay. All right, that's all for me today. If you have no further questions and you're done copying this, you're free to go, and I'll see you tomorrow. All right, take care.
Thank you. Have a good day.
You.
All right, you're welcome. Take care.